This is lecture 12, chapter 4, section 4.3. So up to this point, we've talked about equilibrium in 2 dimensions. Now we're going to jump into equilibrium in 3 dimensions. The way in which we do this process is pretty similar to what well, not pretty similar, it is similar to what we did with 2 dimensions. The only difference is now we have 3D vectors, and our R cross F defined moments is a little more complicated, but otherwise we're still using all the basic tools that we've already learned in chapter 2 and chapter 3. So one of the things about 3D is that the types of reactions that you'll encounter are a little different. I mean, they're the same types, except 3D you have to account for them. So for example, if you have a ball or a piece of material, a rod or a footstool or whatever on the surface and it's frictionless, then you still only have a simple reaction. If you have a cable, you know that the cable is always going to follow the direction away from where it's attached, and so that force again can have IJK components. If you have a roller, then you know that the roller is going to have 3 reactions, except in the direction in which it can actually move. And then lastly, not lastly, but then you have what's called a rough surface. That means that the footstool or the bottom of your stool can now be resisted in motion in both X and Y, and also in Z, depending on how it's attached. So these show you the different levels from probably the least constrained to the most constrained. The fixed support being constrained in all 3 directions with both moments and forces. Those types of problems we'll touch a little bit on in the homework, but for the most part, we don't do those. They get a little complicated for an introductory class. So one other thing also is with the idea of bearings and hinges. So just like I discussed earlier, is when you have this type of structure where you have a bearing, you're only going to be able to support forces and moments in the direction of the bearing, or right, the non-directional bearing. So as I'm saying, any kind of a lateral or axial load will not be supported in general by bearings, and so you won't have to deal with them. Now there are cases where such as the second group, where you'll have bearings that can, and we generally don't deal with those that much in this class. So point is that on an exam or the final, I will tell you what type of reactions there are. Otherwise, you're looking them up. So it's pretty much self-explanatory, and after you do it, you get a pretty good idea of what's what. So what I want to do now is discuss kind of the process of how you solve these problems. And as I said, they're not really different than 2D. You want to start by drawing your free body diagram. That's always the first thing that you're going to do. And it should say determine what you're given, not give, and what you need to find. So as always, good habit to get into is writing your given and finding and writing what you need to find. And then what are your governing equations? So as we found is that in 3D equilibrium, we're going to set up our sum of the forces in the X, Y, and Z, and our sum of the moments about a particular point. And so the examples I'm going to show you in this lecture will be where we find a moment about a point or a line. And that's it, just like we did in chapter 3. So then once we've decided our equations, we need to determine what our tension and force vectors are, and then go ahead, pick the point where we're going to take the moment. That's, as I say, the easiest is to choose the point with the most unknowns. And then solve for tension forces, and then solve for your reactions. So it sounds easy on paper, but let's walk through a problem, and that way you get an idea. So what I've done in this example is I have this example, and I'm actually going to, instead of writing it out in front of you, I'm going to show you each step. So here we have this telephone pole. So you're standing at the very top of it, so it's only 6 meters, so it's not as intimidating as the picture. But you have a single cable at the top at C, and you're given that it's carrying a tension of 455 newtons. And then you have the table BE and BD as shown. So when we want to solve this problem, the first thing we really want to do is the free body diagram. So here it is again. So here's our free body diagram. So what I did is I rewrote the object, and with one with dimensions, the other with just the forces. And so I found with this example, it was easier to do that, to label things and not get too messy. You could have transposed the tensions and the reactions on the left diagram. That would have been fine. So, but if you have a little straight edge, it helps a lot to make these things neat, legible. So there's our free body diagram. So we're trying to find the two tensions that are unknown and the reaction at A. And so because A is what's called a ball and socket, then we know it can hold three forces in each force in each direction, but it cannot support any moments. It's free to spin. So we're not, that's a very common type of reaction that you'll see in a lot of different problems. So the next step is, and I kind of already said this, but what type of reaction is A? So it's a ball and socket. What are the governing equations? We know that if you add the tension BE with the tension BD, force at CF, and A, all of those have to equal 0. And they have to equal 0 in the X and the Y and the Z. We also know that the sum of all moments about any single point also have to be to 0. So first we describe our tension vectors, and this is just right out of chapter 2. We identify our tension BD, tension BE, force CF. And so here where I'm just writing out the general equation, the scalar value multiplied by the unit vector. And the unit vector I've simplified. It turns out that if you take the distances and square roots, you end up with 4.5 in the denominator. And so 1.5 or 4.5 is essentially 1/3, and that's where I get these. So I chose, because these are simple fractions, I'm just leaving them in the fraction. If you want to convert them to decimals, that's fine too. Carry 3 or 4 decimal places, that works. So finally, we have our three equations. We have, obviously, TBD and TB aren't known, so we'll start with those three equations. Then the next step, we're going to pick a point to sum our moments about. Now, because A is a point of interest and it has three unknowns, it makes sense to sum our moments about point A. So if we do that, we know that we need our R vectors. So we know that you could go from A to E and A to D, but then you'd have to do two separate R cross equations. So you can just pick the common point of B. So with A to B is just 3 in the Y direction, or 3J, and A to C is 6J. So what we end up with then is these three cross product equations that we're going to set equal to 0, and they're going to look something like this. So we'll have our 0, 3, 0. We'll put in our vector for each one and add them all together and set equals 0. So once we do that, we're going to go ahead and do our cross product as you would, and you'll get this long string of numbers and unknowns. And the important thing is to make sure that you keep the i's and the j's and k's separate. So when you line them all up, make sure that you label what's I, what's j, what's k. So the next step is to actually solve the individual. So what I did here is, after I did the cross products, I took the I components, all the I components from the cross products, and I set those equal 0. There were no j, which makes sense because there's no rotation about the j based on these forces, and then the k. So with that, I had the two equations, and I was able to then solve directly and get my tensions. Okay. So in a lot of problems, that's all they ask you for, and you're done at that point. But we still want to know what is AX y, and z. So we need to solve for those. So the next step then is just to simply sum the forces. Now, as you can see, the general equation is to sum the forces to be tension BD, tension BE, force CF and A, all vectors has to be 0. So if we go ahead and add up the forces in the X simply by taking the I components, then we can substitute in our values for TBE, TBE, and in each of the 3 equations, we'll just have the one unknown we don't have. And so we solve, we get the 3 values, and our final vector ends up being negative 195 plus 1170 plus 130. And that's it. So mostly it's just keeping track of the numbers, not making a math error. But other than time, it's really, the complexity doesn't really change. It's a few more steps, but after we do a few of these, you'll see how they are very, very similar in their approach. So this is from the example worksheet. So hopefully you downloaded that. That's posted on Polylearn. So here we have this 12 kilogram plate that's sitting at an angle of 30 degrees. And there's the relative distances for each. And what we want to determine are reactions at A, the reactions at B, and that tension T. So we know that given that the B cannot support an axial load, and even if it could, there wouldn't be any. And you can probably see that because the T tension has no X component, no Z component, and the weight of that plate is only in the Y direction, so it has no Z component. So we're not applying any forces in the Z direction. So how are we going to solve this? So here we have the actual drawing. So I've drawn my tension, I have my X, Y, Z. I've labeled the two-body diagram with my AY, AX, BX, BY, tensions in negative X direction. So first thing, I know it's a 12 kilogram multiplied by gravity. I know it's 117.7 newtons. So that's going to use that later. Now, typically on a problem like this, we're going to pick a point to take, like before, is we don't have any vectors per se in this case. So we can then figure out well, we do have vectors, but the directions aren't needing to be found because they're just in the standard directions. But what we can do is we can figure out which point we can take the moment about. So it turns out that if you have something like this, it doesn't matter. You can take the moments about A, take the moments about B. It really doesn't matter what you do. So in this example, I'm going to sum the moments about A. So I know then that if I'm going to do that, if I sum moments about the A, point A to 0, then my governing equation is going to be R, B relative to A, crossed with the reaction at B, semicolon there, and that's going to be plus R, D relative to A, crossed with the tension T, and this point up here is D, and then plus RG relative to A, crossed with the weight. And all that equals 0. And so I labeled this W. Oftentimes this point for center of gravity would be labeled G, so that's probably a better way to do it. But initially, picture I just want to show you. We know that since it's a uniform plate, that whatever weight is there, it's in the geometric center. So there's our equation. Now, we need to figure out what our respective our vectors are. So go ahead, we know that R, B relative to A, if I'm going from A to B, and that's just going to be minus 570 in the K direction. Okay. If I do R, D relative to A, then that's going to be equal to 150J minus 770K. And so the 150, we know that if we're going up in the Y 150 because that's the radius, and then going from A all the way back, if you add everything up, it gives us 770. And then lastly, we have our G relative to A, and that's going to give us, I'm not going to run out of space right next, but our G relative to A is going to give us 100I minus 173.3J minus 285K. All right. So where'd that come from? Well, the 285 we can see pretty easily. That's, if we go, this is 250 wide, so half's 125. So 160 plus 125 gives us 285. And since we're going from here to the force, it's negative. So that's our K direction. This is 30 degrees. So we know that it sticks out halfway. So the distance in this direction, if we look at 200, so this comes from this triangle here. Now the plate itself is 400 millimeters long. So if we go halfway, that's 200 millimeters. So if I take 200 as my hypotenuse halfway, then I know that to get to this point, which is my point G, I have to go down a negative 173.3 in the J, and I have to go out 100 in the X, and that's just based on a 30-degree triangle and the hypotenuse of 200. So there we go. So now we just need to put it all together. So go ahead, and let's go ahead and write that out. So we have this, and voila, there's that. So what I've done is I've just taken the R cross as I did before, putting everything in. So take a second to look and make sure you agree with everything. So once we do that, we'll go ahead and do our cross product. And so once we do that, I'm not going to write it all out, but what I'm going to do is just show you once we, so the next step would be to write it all out and then separate it into IJK. So you can write it all out, but if I separate the I get 570 BY minus 33,345 equals 0. So my BY gives me a value of 58.5 newtons. If I do the J, I get negative 570 BX plus 770 T equals 0. All right, so can't solve for that quite yet because I don't know what T is. So I come down to K. That should be okay. So that's a little K. No, that's a little K. So, sorry about that. And so what we have here, we have 150 T minus 11,770 equals 0. And so we end up with T equal to 78.5 newtons, which we can plug in here, and we get our Bx equal to 106.0 newtons. And that's it. So if we go back now, the only thing we need to go back now is essentially sum our forces in the X, Y, and Z. So if we do that, if we sum our forces in the X to 0 and take our X values, which was what? 1060 and 78.5, then, and those are opposite direction. So we know that we have AX plus BX minus T equals 0. But because BX is 106.0 and this is only 78.5, that means AX is going to be negative 27.5 newtons. It's going to be going the other direction. And if we do the same thing with AY, some of the forces in the Y, then we end up with the Y being AY plus BY minus weight equals 0. And for that, we get an AY, it's positive, because this is 58.5, so the difference between that and 117.7, which was right there, gives us 58.9. So we have 58.9. And one last thing is, even they told you that BX was 0 at the beginning, but they didn't say anything about AX. And so it's important to, even though you know it's 0, it's important to write it. So you can write it just as AZ equals 0, or you can write it as BZ equals AZ equals 0. The double equals is okay in this case. It's still heresy in some worlds, but we'll let it slide. Okay, so that's that problem. So hopefully you see the similarities to that compared to what we've done before in the previous problem. Oops. Now, here's another example, and I picked this not because it's different than the other one, because I don't want to just do 10 of the same problems. But what we can see in this one is a slight variation in how we can solve. Now, for one, is you can do this problem using R cross F, just like we did before. But you have to look at what they're really asking you for. And so they're asking you for the same things. They want to know what the reaction is at A and B, and they want to know what the force F is. And so, again, you could do R cross F, but sometimes, depending on your learning style and whatnot, it might be easier just to look at the direct force times distances. So let me show you what I mean by that. So here is the problem. Not really a problem. Here is the fun challenge. How about that? So what I've done is I've drawn the free body diagram. We know that Z is up, X is out, Y is to the right. And there's my respective distances. And so how are we going to do this one? Now, because everything is orthogonal to in terms of the forces, we can just sum moments about the X, the Y, and the Z and some forces to solve. We don't actually have to do an R cross F per se. So for example, when we first try to solve this for F, you'll notice that if we look at the diagram in general, you have W is going down, and it's 0.1 meters away. AX, AZ, BX, BZ are right on the Y-axis. So if we sum the moments about the Y-axis, those don't have any bearing because their distance is 0. But you notice how the W, it wants to make a counterclockwise rotation. So if this is the positive Y, it wants to do this counterclockwise. So W times 0.1, and then F wants to go the other way or clockwise, minus F times 0.2. So we can see right away that the relationship is just that whatever that force is, it's half of the weight, and that's just the mechanical advantage that we get from doubling the moment arm. So if we do that, then we can calculate it right away. Now we know that we have, this is 75 kilograms, which if we multiply it by gravity gives us 735.75 newtons. Okay, so then we know that, or for that the force is equal to 367.875 newtons. And I'm carrying extra sig figs, we don't need to, but so F is really 368 newtons. Okay, so we get that right away. So now let's look what else we can do. Now, if we sum our moments about the x-axis, notice that since AX and AZ are on the x-axis, that'll make them disappear. We're summing the moments about the x-axis, so a parallel force isn't going to create a moment. So then that's going to allow us to solve for BZ, because we know that the weight is going to want to rotate clockwise about x. BZ, if it's written that way, is going to want to go the other way. The force being where, because the force is coming out in this direction, it's in the x, it's not going to have any bearing. So really it's just a relationship between this weight and BZ and their respective distances. So if we write this out, we have BZ times 1.1 meter minus W times 0.6 meters. That's the difference. And so we plug in our value, and when I was doing these, I plugged in, I left the extra decimals. We get BZ is 401.318. So, or essentially 401 newtons. And so we know BZ now, so we can go ahead and let's do the same thing. If we sum the moments about the z-axis, which we know is here, it's going to again exclude AX and AZ. And the only thing that really counts then is going to be BX and F, because W and BZ are in the direction. Now, right away, we can probably surmise that BX is going to be opposite of F, otherwise we'd have a net rotation of one direction, because we've already established that F is coming in this direction. So if we write BX, assuming it's negative, then we're going to say BX, keep some space, sum the moments about the Z0, and that's going to be BX times 1.1 minus F times 1.3 equals 0. And we get BX equal to 434.76 or 435 newtons, but it's in the negative direction. So we can write it as negative, or we can just write it like this, however you want. And so, but the point is that BX is going to be going in this direction. But again, don't change your free body diagram. It gets real confusing. Just leave it. I just did that for illustrative purposes. In your final, and so what we'll do is we'll leave these as they are now, and then to make sure that it's clear, especially when you turn it in on an exam or final, you're going to box all the answers at the bottom. So now that we know everything here, the only two unknowns we have left are AZ and AX. So now we can just quickly sum forces and find those. So if we sum the forces in the X to 0, we know that F minus BX plus AX equals 0. And so if we end up with 367.8 minus 434.7 plus AX, we end up, and since this number is less than that, this is going to have to also be, AX is going to be positive, or it's going to be negative, right? Because we want, wait, x is going to be, yeah, x is going to, because of the way we have things going, we have bx is going backwards is negative, and because bx is bigger, we end up with this number. We end up with ax being 66.9. Sorry, I misread my own notes. So we have 66.9. So there's that. And then lastly, if we sum the forces in the z to 0, we get bz minus w plus az equals 0. And that's going to give us 401.318 minus 735.75. And you don't have to carry all these if you don't want, plus az, because again, as long as you're within a percent or so or less, you're close enough for government work. So az equals 334. So what we get, what I would recommend is if this was a problem on a test, they're all done, I would just write it out like this, ax, az, and just put your appropriate number, 66.9 with the proper sig figs, 334 newtons, and then bx, bz, bx being negative 435 newtons, 401 newtons. And then, of course, F, 368 newtons. And there you go. So I'm writing a little quicker. It's not as neat as some of the other stuff, but the point is that you get everything down. It's legible. You can see it. This hopefully has a Z, not a 2. But that's how you do it. So we didn't really need to do R cross F. This is a pretty simple problem in that sense once you saw what you're actually being asked for. So I have one more problem in this lecture, and this one here. Now, in this problem, you have this plate, and it's welded together at the joint, and you have just a single force, the 80 pounds at A, and this is held at D and B with the ball and socket joint. So as you can imagine, if you can physically think about this, the 80 pounds is going to want to cause, in order to prevent motion, if it's free to rotate about B and D, it's going to want to cause C to push down. It's going to push down on the ball at C. But because this is just a ball, we just have a simple reaction. But we have to account for the fact that we have 3 reactions at D and 3 reactions at B. So how are we going to do this? And you may already have an idea based on what I said earlier. So there's the drawing. And here's the schematic of it. So again, you have just a single force CY here. We know that the entire width down here is 8 inches. We know this distance from A to B is 6. This is 12. The height is 9. So then the question is, how do we solve it? What are we going to do? So, well, just like we sum moments about a point to get rid of unknowns, we can also sum moments about a line to get rid of unknowns. And so if I go ahead and draw a line from here to here, then if I sum the moments about that line, then I only have one unknown, don't I? Eliminate 6 of them. So whenever you see a problem like this, and there is one on your homework like it, where you have something supported by 2, you'll never get something with 3, because then there's too many unknowns and it's indeterminate. But if you have 2, then just simply draw a line between it. And so we know that for a governing equation, we know that the moment about this line, dB, equals lambda dB dotted with R cross F. Right? And that's just the governing equation from chapter 3. Now, it turns out that you may recall from chapter 3 that when we said dB, we always went from D to B. And so here, because I chose a line, how do I know if I'm going from D to B or B to D? Because we found in chapter 3 that depending on the direction you went, that would change the magnitude of the final answer. It would either be negative or positive. So it turns out that in a problem like this, it doesn't matter. It won't have any influence. So if you write your unit vector like this, or from D to B or B to D, it's going to be of no consequence. So we know that we need this, this, and this. So let's go ahead and figure those out. So we have lambda BD, or I'm sorry, lambda DB for consistency. Actually, I'm going to say lambda BD because that's how I did it in my notes, and I don't want to have to think on the fly. So just pretend this was BD. Always write with the eraser when you do. Either way works, but I should have saw that. So there we go. So lambda BD. And if you want to pause at this point and solve yourself, feel free. I think you, at this point, you have everything you need to do the problem. But otherwise, I'm going to say negative 8I minus 9J plus 12K. And that's all divided by 17. That's just the magnitude. So I'm just going to leave that in form 8/17, 9/17, 12/17. And then what's my R? R, A relative to B, because I want to go to the nearest point of the line, and that's my only force, so it makes sense. I'll just go there. So that's going to be equal to minus 6I. And then I also need to do RC relative to D, and that's going to be equal to 8I. Okay, so this is the governing equation, but remember that unlike where we say M equals this, in ours, we're going to say we have to set all this equal to 0. So we're going to say lambda BD dot R, and in this case, we'll say A relative to B, crossed with, we'll say the force at A, so we'll just say A, plus lambda BD dotted with R C relative to D, crossed with C. And that equals 0. Sorry about that space. So this whole thing plus this whole thing equals 0. And that's the big difference. So we're not just solving this. This is our governing equation, but you have to do this in order to solve, just like before. So we have this, we have this. We know that our force at A, we'll just call FA, is just equal to 80K. And we know that C just equals, it's just in the J direction. So we can call it CY. So we have everything. So let's go ahead and set it up. And so what do we end up with? We end up with this. And there you have it. So here's my unit vector for the line, my R vector, that. So you see a lot of it's 0. It's going to simplify down pretty easy. So what we end up with is negative 9/17 times 480 plus 12/17 times 8 times CY equals 0. And we end up solving CY is 45.0 pounds. And that's it. So quick review. We started out essentially the same approach. Got rid of those 6 unknowns, equation for our line, our unit vectors. The important thing to remember is this. So you may ask, if on an exam, how are you going to know the difference? Well, if you're asked to find a single letter, or I won't be that vague. I'll say if you're asked to find a reaction, then you know you're in chapter 4. If you're asked to find a forced couple or a moment or moment without a line, moment without a point, then you know you're in chapter 3. So that's the big difference. So I hope this was helpful. We have one more lecture before the exam, and that's just going to be a few more problems like this, and we're done with chapter 4. So please, and the homework is posted, so hopefully you get a start on that. The test will be next week, the week of the first week of May, and I will put some more information on that online. Thank you, and have a good night.